Hello, my name is IJCNLP, and I'm going to talk about a joint work with Shu and Jiang about extracting Definienda from mathematical scholarly articles with transform-based approaches. So Definienda means terms defined within a definition. So this work is in the context of a larger project where we aim at extracting semantic information from research articles, and in particular research articles from the mathematical domains. The observation is that there are a lot of structured statements within a mathematical paper, such as axioms, theorems, proofs, definitions, etc. And traditional ways of navigating the scientific literature only allows you to do things like keyword search or navigating papers cited by another paper. They don't allow you to actually exploit the structure of a mathematical paper. So this overall project aims at better knowledge discovery from mathematical papers. We don't assume anything else that we have access to the PDF version of the article. And in this particular sub-project that I'm going to talk about today, we want to extract terms defined within a mathematical definition, which is called the Definienda. So we assume that we have a mathematical definition in PDF. We are going to extract the text of the mathematical definition, and we want the task is to identify what are the terms defined within this definition. So this is an example of mathematical definition as it may appear in a mathematical paper. You have at the top the PDF version rendered as a bitmap, and at the bottom the LaTeX source. But for the task itself, we will not require the LaTeX source. And so you see that in this particular definition, I can extract its text. Its text looks like this. We have two terms that are actually defined, the term spread and the term components. We know that the terms defined because the language tells us that. We say that the collection of subspace is a spread. This means that spread is defined, and similarly for components. And we also had a clue in the PDF in the font used for these terms, which was in a different font, non-italic font with an italic definition. This is another clue, but that we will only exploit to build a data set, not for the task itself. For the task, we don't assume that we have access to the font-based information. And so the goal is to extract spread and component from such definition. So for our approach, first we built a label dataset that is available online. You will find the link in the corresponding paper. And so the goal was to have a high quality dataset that is not necessarily complete. The goal is to have a high quality pairs of definitions and definienda, not necessarily to extract all the definitions within a collection of articles. So we collected articles from arXiv in the area of combinatorics, and we obtained both the PDF and the LaTeX source of the PDFs. From the LaTeX source, we extracted the definitions that were within a definition environment. So not all definitions are within a definition environment, but that's fine. Our goal is not to extract all the definitions, but only to build a high-quality dataset. And within these definitions, we looked at clues such as the use of italic or emphasis to indicate what the definienda were, as well as optional arguments to the begin definition environment, which is sometimes used to identify the defined term. Again, not all definitions use such clues, but that's fine. Our goal is, again, to only obtain a subset of definitions and the definienda that is of high quality for building a dataset. And after cleaning up some common noise of, for instance, common text that is set in italics, but it is not a definiendum, we obtained a dataset which we examined by hand. On a sample of 1,024 entries, we found that only 30 of them were incorrectly labeled. So this indicates that our dataset is of high quality indeed. We manually corrected these 1,024 to obtain a test dataset of around 1,000 labeled definitions with definienda. And the rest of the dataset that has not been manually cleaned, but it is still of high quality, becomes the training data. So our main approach will be to fine-tune a language model for the task of token classification, classifying every token into whether it's part of a definiendum or it's not part of a definiendum. So we are comparing two different general language models. One is Roberta, very commonly used, and one is a domain-specific model that is built to be a language model specific to the domain of mathematical papers. So we experimented with a different number of samples for the fine-tuning task to see the performance of the classifiers with low resources. And then to evaluate the prediction, we compared the extracted terms based on the IOB2 tagging with our gold standard in our label dataset. So this is the first category of approach. Another category of approach was to use a much bigger language model, GPT, which is trained for to answer prompts, and to give not to fine-tune it, but to give a prompt of the language model that tells the language model to extract defined terms in the definition, and giving an example of the tasks that we want to do. So you have here an example of the prompt and of the answer of GPT 3.5 and GPT 4 on this particular task. You see in this particular example that GPT 3.5 extracts way too many things from the definition. GPT 4 is actually providing a perfect result. So here are our results. So you see for every particular model, so GPT 3.5, GPT 4, two different variants of the model that was fine-tuned on mathematical data, depending on how many text it was initially trained. And on Roberta, you see the amount of training data, so which is only one for GPT, and here in these results, 10,000 for the other three language models. And you see the precision, recall, and the F1 measure summarizing both. So you can see that the main message is that it is possible to achieve a relatively good F measure, in particular with Roberta, the Roberta language model. GPT-4 is also quite good, even though it's not fine-tuned for this task. GPT typically have a much higher recall, but a lower precision than regular language models that have been fine-tuned. And in particular, GPT 3.5 has a terrible precision because it extracts too many results. So this is our general conclusion. Fine-tuned classifiers have more balanced precision recall, and also, not to forget, there is a much smaller cost in training them. GPT's answer have better recall but much poorer precision. GPT-4 shows quite impressive results for this particular task. We intend to test on a broader, more diverse dataset of PDF papers. We intend to try to link terms in a paper to the definition, and to improve the robustness of the domain-specific language models over different tasks beyond the tasks that we have here. Thank you for your attention.